So welcome to the second module. In this module, we will discuss the main theorem, Stone Weierstrass Theorem, and its proof. So let us begin our discussion. So what does this theorem says? This theorem says that if K is a compact space and A is a subset of space of continuous function over K, which is a unital subalgebra of Ck, and it has a property that it separates the points of K, then A is dense in space of continuous function over K, that is Ck. And there is an equivalent argument of this theorem that if A is unital subalgebra of Ck, which separates the points of K and is closed, then A equals to Ck. So these two statements are equivalent. If you say the first statement, then second statement is true. When we say second statement is true, then first statement itself is true. How these two statements are equivalent, let us see first. We will prove the second statement, and by proving this second statement, first statements will also be already proved. So let's suppose that first statement is true, then how second statement is true? Suppose that K be a compact space, is a unital subalgebra of Ck, and it separates the points of K, then A is dense in Ck. Now for second statement, we have to show that A is equal to Ck whenever A is unital subalgebra. It separates the point of K and A is closed. So suppose A is unital subalgebra, it separates the points of K, it is closed. So A itself a unital subalgebra and separating points by the first argument, A closure will be equal to Ck since A is dense in Ck, and since we already supposed that A is closed, and whenever A is closed, then A closure will equal to A, so A itself will equal to Ck. It shows that the first argument implies the second argument. Now we'll see the reverse. Let us suppose the second argument is true. Now we'll show that the first argument is also true. Suppose that A is unital subalgebra of Ck, separate the points of K and is closed, then A is equal to Ck itself. Now we have to show that the first argument is true. It means if A is unital subalgebra separating the points of K, then we have to show that A is dense in Ck. It means A closure is equal to Ck. So we'll look upon the A closure. So suppose A is unital subalgebra and it separates the points. When A is unital subalgebra separating the points, it means A closure is also an unital subalgebra, since A closure already contains A itself. So it also separates the points of K. So A closure set has both properties. It is unital subalgebra of Ck separating points of K, and it is closed. Since A closure is closed, it means by second argument A closure is equal to Ck, and when A closure is equal to Ck, it means A is dense in Ck, and hence second argument also implies the first argument. It means both of these arguments are equivalent argument. Now we will look upon the proof of this theorem. So first of all, suppose K is a compact set, and we denote Ck as to be a space of or set of the continuous functions f from K to R equipped with the sup norm. Sup norm is defined to be norm f infinity that is equal to supremum of modulus of ft, t varies in K. And now we see that A is a unital subalgebra. So when we say that A is unital subalgebra, It is unital subalgebra if the constant function 1 is in A, and whenever we take f and g in A and take any alpha beta from a real number R, then alpha f plus beta g should be in A, and their multiplication f into g also should be in A. Then we say that A is unital subalgebra of CK. And when 1 is in A, then all constant function f is equal to c will also be in A, because c is nothing but c is equal to c into 1, and 1 is in A, c into 1 is also in A for all c in R. And the second thing that we said that A is separating the points of K, means A separates the points of K. What does it mean? It means that you take two separated points from K, S and T namely, then you will have an element F from A. A separates the points of K. It means take two separated points from K, S and T, then you can have an element F from A such that F take the different value at those separated points. F of S is not equal to F of T. It means A separates the points of K. So these things are clear now. And now we see that set of polynomials over K is nothing but a special kind of unital subalgebra of CK. Why? Because we know that 1 is itself a polynomial. If you take two polynomials P1, P2, then alpha P1 plus beta P2 will also be a polynomial for any alpha beta in R. And if S and T are two different points of K, and then we take P of X is equal to S, or P of X is equal to T, constant polynomial, then PS is not equal to PT. Sorry, not constant polynomial. Take Px is equal to X itself, not S. Identity polynomial. Then P of S will be S and P of T will be T. Then P of S will not equal to P of T. Okay. Now, let A be a closed unital subalgebra of CK which separate the points of K. This is the hypothesis of the theorem. So to show is that A is dense in CK. A is dense in CK means for given F in CK, an element F in CK, and any arbitrary epsilon greater than 0, we have to show that there exists an element G in A such that F minus G with respect to the sup norm is less than epsilon. It means you take any continuous function over the compact set K and take any epsilon greater than 0, then you will get an element of A, G in the epsilon neighborhood of F with respect to the sup norm. Now consider two elements S and T from K such that S and T are not equal. As we consider that A separates the points of K, and hence there exists an element H from A such that H of S will not equal to H of T. Now for any lambda mu from R, consider a function H nu H tilde which sends nu to mu plus lambda minus mu times H nu minus Ht by Hs minus Ht, and you see that these quantities H itself in A, H minus H nu minus Ht will also be in A. So H nu minus Ht will be element of R, and these are the element of A itself. Their addition multiplication will be element of A. So H tilde will be an element of A, and when we put S in place of nu, then H tilde of S will give the value lambda, and H tilde of T will give a value of mu. So this lambda and mu is an independent choice depend upon us from the real values, real numbers. So taking lambda to be Fs and mu to be Ft, Then we call h tilde this function as f subscript st. Then we see that fst at the point s give the value fs, and fst at t give the value ft, where fst is an element of A. It means what? It means we are able to find a function fst in my set A, which at two distinct arbitrary points s and t gives really the values of f at those points. Thus, s not equal to t implies there exists an element fst in A with the property that fst takes the value fs at s and fst takes the value f of t at the point t. You see here this in this figure. Uh, this figure is not real figure. This figure is in we can see this figure is valid in r square. So you can see this figure to illustrate the proof. To just visualize the proof, uh, here we take s and t, two distinct points on real line r, which will belong to some closed interval that is compact, and this is graph of f. This red line in between is the graph of f, and this dotted line above is graph of f plus epsilon, and this below dotted line is f minus epsilon. So this region in between these two dotted line is nothing but the epsilon neighborhood of this function f. See, the epsilon neighborhood of a point in real line r is open interval, and epsilon neighborhood in r square, that is plane, is open circle. But when we talk about the epsilon neighborhood of this function, this looks like this. Then we say that there exists a function fst. So suppose this is a function, this blue line is the function fst. It takes values as same at point s as given by f. So at this point, this function fst at these 2 points takes the same value as function f does. So these 2 points are the good points. So at these 2 points, if we take the difference of f of s and fst minus s and at t, then that difference will be 0, which will be less than epsilon for given any epsilon greater than 0. So these 2 points are the good points, but in the different points in this area, this function goes up than f plus epsilon. So here these points behaves as the bad points. So it goes beyond the epsilon neighborhood of f. So we need to find a function such that that function lies entirely in this epsilon neighborhood, and that function will fall in A itself. That is goal to prove in of this theorem. So now for any fixed s, let us take a set mu t. Call a set mu t to be the collection of nu from k, collection of v. So, v is an element of k such that fst at v is strictly less than fv plus epsilon. Then those points are called to be mu t. See how you can visualize this. As we see in earlier picture, this is fst. Okay, this is f plus epsilon. The upper dotted red line is f plus epsilon. So the part of the function which lies below that f plus epsilon, this one, so the points corresponding to this part, that is these points and these points and these points, collect all those points and call those points to be the set mu t. So mu t is the set of those points where function takes values which is strictly less than f plus epsilon. Okay, so we take this mu t, and mu t is the pre-image of an open set with respect to the continuous function fst. So mu t is open set. You can actually visualize here also that mu t is nothing but the union of these small open intervals, and union of open intervals is open interval itself, which is open set in R2 case. In general case, mu t is the pre-image of open set with respect to the continuous function fst, and we know that if f is continuous function, then pre-image of open set is open as the characterization of continuous function, as we have seen in the first lecture. Hence mu t is open set, and t at t fst is equal to f of t, and f of t is less than f of t plus epsilon for every epsilon greater than 0. It means t also lie in this mu t. So mu t is an open set containing t. It means mu t is an open neighborhood of t. Then collect all those mu t's for every point of k. Union of mu t, t varies from t from k, then it will become an open cover of k. And now compactness plays an important role here. Since k is compact, so each open cover will have a finite subcover. So there exists a finite subcover. There exists t1, t2, and tn finitely elements from k, such that k is equal to union of mu t I varies from 1 to n. This k is not subset, it is equal to sign because k is the bigger space itself. So nothing no union of subset of itself can greater than itself. It can maximum equal to itself. So k is equal to this union of mu ti. Now we had already taken mu t and corresponding to those ti's and corresponding to every ti's we will take different fti's. Okay, so there are finitely fti's, then we take the minimum of fti's, I varies from 1 to n, and call this function to be h of s. And by our previous lemma in this the first video lecture, that if f and g are an element of a, then their minimum will also be an element of a. We had proved this. So this finite minimum of finite terms of a, that is h of s, will also be an element of a. We can visualize h of s by this figure here. You see here we take different functions. First of all, we take this pink color, this function as fst1. Okay, first we fix s here, s is fixed, and we take an element another point t1 here. Then we get a function fst1 from a, which takes same value at s and t1 as the function f does. Again we take another point t2 here, suppose here is t2, then corresponding to that t2 we get another this black line function fst2, and this fst2 also takes the same value at s and at t2 as f. And for t3, this blue line is fs3, and this fs3 also takes the same value at t3 and s as f does. So in this way we take this t1, t2, t3, so there are n points were taken. So I only showed 3 points here. So likewise we can take n points here, and then we take the minimum of all those fti's. So in these three functions, the function lying below, the lowest position of the function, we take those parts. So this part becomes the minimum of all those fi's. So call this function to be minimum of fsti as h of s. So we had done the half part of the theorem, the half part of our exercise, that we want a function which lie within this epsilon neighborhood. Now we had taken a function which lies beneath the f plus of epsilon. This h of s lies beneath f plus epsilon. Now after doing some calculation, we'll find another function by using these hs, that function will lie within this interval. We'll do in next slides. So we got that h of s is an element of a, and at value of hs at s is f of s itself. See, each fsti's take the value f of s at point s. So the minimum of all those fsti's will be among of them. So its value will also be fs. So value of hs at s is f of s itself, and h of s is strictly less than f plus epsilon, as it is clear from the picture that I have shown you. Why this is strictly less than epsilon? We'll do by calculation also. Since hs of nu is nothing but the minimum of fsti's take it at point nu, and each fsti are less than f plus epsilon. So all of this minimum, since we had shown that hs is the minimum of fsti's, and each fsti's are strictly um, less than fv plus of epsilon. So this will be less than f plus of epsilon. Okay, here you can see that this h of s is the minimum of all those fsti's. Okay, okay. And for what values? We take those values nu from union of mu ti's. Union of mu ti's is nothing but the k, and mu ti is the set that we had defined here. Here mu t. Mu t is the set of points where fst is strictly less than fb plus epsilon. Okay, and here so this minimum value of fsti at the point nu, which is an element of this union of mu ti's. So this will be among some of mu t's. So this total value will be strictly less than fb plus of epsilon, and hence h of s will be strictly less than f plus of epsilon. So we have done one part and we get these 3 points here. Again, we take nu s to be the collection of v element of k such that hs of v is strictly greater than fv minus of epsilon. Okay, so we take one hs, and again we change another, we take another s, we take another hs, and each hs is less than f plus of epsilon, and we take the points where hs take the value greater than fv plus epsilon. So overall this minimum and maximum will give a function which lie within that interval f plus epsilon and f minus of epsilon. So this is how beautiful is this. So this vs is also an open set because it is an inverse image of open set with respect to the continuous function hs. And we see that the value of hs at s is f of s, and f of s is strictly greater than f of s minus epsilon, since epsilon is a positive quantity and we subtract the positive quantity from f of s, then f of s will be greater than f of s minus of epsilon. So this s satisfies this condition for being in nu s. So s is an element of nu s. Now we take the union of all nu s varies in K, then this will become the open cover of K. Now K is compact and hence again we have a finite subcover. That means there exists S1, S2, Sm in K, these finite points in K such that K is equal to union of nu sj's. Okay. So now again we got a finite subcover of K and different points, that is finite points S1, S2, S3 and Sm. Now with respect to all those finite SIs S1, S2, S3, Sm, and with respect to each of those Sj's we will have HSJ, and then we take the maximum of HSJs. J varies from 1 to m and call this as G, and G is nothing but the maximum of elements of A, so G will also be an element of A, again by using the previous lemma discussed in our previous video, that when F and G is in A, then their maximum is also an element of A and hence G is an element of A. So we can see this in this figure also. You can easily understand what is being discussed here. See, for we have S1, S2, S3, S4. I have taken only 4 points here. So likewise we have Sm also. So corresponding to S1 we have HS1. Corresponding to S2 we have H of S2. Corresponding to S3 we have H of S3. Corresponding to S4 we have H of S4, and so on and so forth. And again we take the maximum of all those hxi's. We take the part of the function which lies above all those functions, that is this part. This part becomes the maximum of all those finite number of functions, and call this function as G to be the maximum of HSJ's. J varies from 1 to m. 1 to m. Okay, so this is G. By this picture you can see that G lies entirely above this dotted line below, which is f minus of epsilon, and also lies with below this f plus epsilon and lies above this f minus epsilon. So this is required G which we need to find for proving this theorem. So G is strictly greater than f plus of epsilon. Why? Because at point nu, an arbitrary point of the K, where K is equal to union of nu sj's, nu is in K, so nu will be in sum of nu sj's, and each nu sj's, h of sj is strictly greater than f nu minus epsilon. So this h nu will be strictly greater than f nu minus epsilon. It means G is strictly greater than f minus of epsilon, and that is this. And for any fixed value of a fixed point x in K, we saw the value of Gx to be the maximum of HSJs at x. So this maximum of HSJ at x, j varies from 1 to m, will give one of them. So there exists w in 1 and m such that this maximum value will equal to hsw of x. And this value is strictly less than f plus of epsilon. We had shown that hs is strictly less than f plus of epsilon in 3. in this here, we had shown that h of s is strictly less than f plus epsilon. So we use that fact here, that hsw at taken at point x is less than f plus of epsilon, and hence g of x is also less than f plus of epsilon for each point of k. So g is nothing but less than f plus of epsilon. Now also it is greater than f minus epsilon. So g of x at a specific point is greater than fx minus epsilon and strictly less than f plus of epsilon, means modulus value of f minus g taken at point x is strictly less than epsilon for every x in k. Now when mod f minus g is strictly less than epsilon at each point, it means its supremum value will also be less than epsilon for taken at every point x from k, and that is nothing but the subnorm of f minus of g. It means subnorm of f minus g is strictly less than epsilon. So this is the required to prove this theorem. Hence we had already proved the theorem. Now we'll show some corollaries. The first corollary, that we have seen that the k is compact space. So we'll restrict that k to be the compact space of finite dimensional space for say it is of Rn. So suppose X is a compact subset of Rn for some n from natural number, then the algebra of polynomials, call it Pxr, means real valued polynomials from X to R, in the coordinates x1, x2, xn. Since we are talking about n dimensional spaces, so we will have n coordinates of this polynomial. It will be dense in space of continuous functions over the compact space X. It is real valued continuous function space. So when we take value of n to be 1, then this Rn will become R, and this X will be a compact subset of R. Then polynomials over this compact subset of R will become a dense set in set of continuous function over the compact set of R, and that is nothing but the classical Weierstrass approximation theorem. So the classical Weierstrass approximation theorem is nothing but a corollary of Stone Weierstrass theorem. So this Stone Weierstrass theorem, the proof of this Stone Weierstrass theorem will be a second kind of proof of the classical Weierstrass theorem. There is uh, already a proof of this classical Weierstrass approximation theorem given by Weierstrass that uses Bernstein polynomials. But here Stone Weierstrass theorem, it doesn't use any Bernstein polynomials. It uses the pure and all abstract structures, and very beautiful proof. So we can prove that classical Weierstrass theorem by this proof also. And the second corollary, this is a result similar to Weierstrass approximation theorem in the theory of Fourier series. Uh, that is in Fourier analysis, we have a similar theorem related to the Weierstrass approximation theorem, which says that the set of all trigonometric polynomials denoted by tau p R to R, means trigonometric polynomials whose domain is R and codomain is also R, is uniformly dense in a space of 2 pi periodic continuous functions on R denoted by C periodic 0 to, it will be 0 to 2 pi, not 1, that is type error. Here C per periodic 0 to 2 pi is defined to be the set of functions f from the interval 0 to 2 pi to R such that f is continuous, and it is 2 pi periodic. 2 pi periodic means the value of f at 0 will equal to value of f at 0 plus 2 pi, that is 2 pi. And it is a subset of set of continuous functions over this closed interval 0 to 2 pi. And each function in this C periodic 0 to 2 pi, not 1, it is 2 pi, can be extended periodically to all of. You can extend this. You take the part of the function lies in the 0 to 2 pi interval and repeat that function in right side and in left side likewise, then you will get extension of that function, and it has the property that is 2 pi periodic. So these elements of the trigonometric polynomials, real value trigonometric polynomials, are the finite sums of the form. Now what is a trigonometric polynomial? Trigonometric polynomials are this specific type of polynomials and are of this form: ft is equal to a naught plus summation of ak cos kt plus pk sin kt, k from 1 to capital N. These are the trigonometric polynomials, and these trigonometric polynomials are dense in C periodic 0 to 2 pi. We identify this C periodic 0 to 2 pi with C PR 0 to 2 pi interval. As we know from the topology that 0 to 2 pi is topologically equivalent to the unit circle in R square. We can have a map which sends t to cos t sin t, then this 0 to 2 pi will map to this unit circle t, which is a collection of ordered pair xy in R square, not R, where x square plus y square is equal to 1. So this is unit circle having radius 1. Now t, that is the unit circle in R square, and unit circle in R square is complex set, and the trigonometric polynomials on t in the coordinate xy is unital subalgebra of CTR, space of continuous function over this complex subset T. Of course, it is real valued. So from the corollary 1, we can say that taking value n is equal to 2, this space of trigonometric polynomials over T is dense in space of continuous function over this unit circle. It means space of continuous function over 0 to 2 pi, which is 2 pi periodic. So these are two corollaries. Now there is also another version of Stone Weierstrass in complex analysis. Not another version. This is a complex version of Stone Weierstrass theorem. We need only one extra thing for proving, for making this for extending this Stone Weierstrass theorem in complex situation, complex field. Let K be a compact space. The complex version of Stone Weierstrass theorem says that suppose K be a compact space and denote CKC to be the collection of all continuous functions from K to complex plane C, complex space C, complex plane C, equipped with subnorm, and take A to be a unital subalgebra of CKC, and it separates the points of K, and it has a property that whenever F is in A, then F bar is also an element of A. That is the extra point that is not there in the Stone Weierstrass theorem in real valued case, in real version. So for complex version, we need this, that when F is in A, then the closure of F should also be in A. Whenever this happens, then A is dense in the space of continuous function over K, which is complex valued, space of complex valued continuous function over K. Now we see the proof of this theorem. This is very easy proof and very small. It uses the Stone Weierstrass theorem that we had already proved. Suppose A is an element of A, then the real part of F, suppose F is an element of A, then real part of F is defined to be, it can be written as F plus of conjugate of F divided by 2, and imaginary part can be defined as F minus conjugate of F divided by 2, and both of these will be an element of A because F and F bar both are given to be the element of A. Whenever F is in A, then their addition is also in A, and division by a scalar alpha to be equal to 1 by 2 will also be in A, and hence this real part is in capital A because A is immutable subalgebra. Likewise, this imaginary part of F will also be an element of A. Now, we take AR to be the unital subalgebra of A containing all real valued functions. Since capital A is given to be the subset of complex functions, so we take the real functions from that space and call it AR. That is a subset of A which contains only real valued functions and all real valued functions, which is a unital subalgebra of A. Now AR will also separate the points of A. AR will be real valued collection of real valued function, which is unital subalgebra. And if we show that AR also separate the points of K, then we can apply Stone Weierstrass theorem over AR. Then AR will become the dense in space of continuous function, space of real valued continuous function. So how we show that AR is separating points of K? So take any two separated point x, y, and k. Since capital A is given to be separating points of k, so there is an element f in A which separates these 2 points x and y. It means fx and fy are two different values. Since f is an element of A which is complex function, complex valued function, so f will be equal to nu plus iota nu. Sorry, this is iota, mistakenly I have written like this, it's tabular. So f is equal to mu plus iota nu, where mu is real part of f and nu is imaginary part of f. Since f of x is not equal to f of y, hence 1 of mu x mu y or nu x nu y should not be equal to, so 1 of mu x not equal to mu y or nu x not equal to nu y will be true. Otherwise, if both will be equal, then f of x itself will be equal to f of y, which is not the case. Hence, one of them should not equal. And whenever one of them will not equal, then that since imaginary part and real part is an element of A, so this mu also nu is an element of A, and one of them separate the point of x means AR separate the point of x. And we apply the Stone Weierstrass theorem. Now we can apply Stone Weierstrass theorem on AR for the real valued functions. AR, so AR become the dense set in space of real valued function over the compact space K. And since capital A is a collection of complex functions, so capital A is equal to space of set of f plus iota g. Here it will be iota, where f and g are from the elements of AR, and AR itself dense in CKR means AR will be dense in CKR plus CKR iota CKR means A is dense in complex valued functions over K. Hence, this complex version of Stone Weierstrass theorem also uh, proved. And one remark here, I want to mention that this is iota, so I write it here. This is iota here, and here also this is iota. This is the set. Okay. Okay, thank you.